In this lesson, we will learn about the sum, difference, and cofunction identities. And to begin, we're going to talk about the sum and difference identities. Now, in the past lesson, we learned identities, Pythagorean identities. We learned some other ones as well. And here, what we're doing is we are working with cosine, sine, and tangent of when we add or subtract two different angle measures. So the first one here we see is cosine of x minus y. So the angle is x minus y. It's two different numbers subtracted from each other. Now we're not going to take the time to go through and prove each of these. So just for now, we're going to tell you what it is and then how to use them. So here, the difference identity for cosine says that if we have cosine of x minus y, we have cosine of x times cosine of y plus sine of x times sine of y. And then if we had cosine of x plus y, we would have cosine of x times cosine of y minus sine of x times sine of y. So the goal is to have these memorized. So you want to take some time either now or later to memorize these different identities. But some helpful tips that might help you to memorize them is with cosine. So with cosine, the cos goes together. So it kind of rhymes, right? Cos goes together. So we have the cosines go together for both of these, whether it be plus or minus. So the cos go together, and then we have the sines together. All right, over here, sine of x times sine of y. And then notice the signs are changing though. So we have, if it's minus y, x minus y, the sign changes to a plus. And then if we have x plus y, it changes from plus to a minus. So the signs are opposite. Now next we have sine. We have sine of x minus y and sine of x plus y. Now with sine of x minus y, we would take sine of x times cosine of y, and then minus sine of y times cosine of x, or cosine of x sine of y, same thing. And then if we have sine of x plus y, we would do sine of x times cosine y, and then plus cosine x times sine of y. So make sure you have these two memorized as well. And a way that you might find helpful to remember is with sine, the signs stay the same. Meaning if it's a x minus y, we have a minus sign here. The sign stays the same. And then if it's x plus y, so the plus stays the same over here. Whereas cosine, it did not. It changed. And remember we said the cosines, so if you're up here with the cosine identities, the cos goes together. Down here with sine, the cos do not go together. And we have sine and cosine paired up on the left and the right side of the plus or minus sign. So again, make sure you have these memorized. And then we also now will extend this to include tangent. So tangent, if we have tangent of x minus y, what we do is we take tan of x minus tan of y on the top over 1 plus tan of x times tan of y on the bottom. And then if we have tan of x plus y, we would have tan of x plus tan of y over 1 minus tan of x times tan of y. So a way to help remember these ones is we have tan of x minus y. On the top is going to be basically the same thing, tan of x minus tan of y. And then same thing for tan of x plus y. The top looks basically the same, tan of x plus tan of y. And then on the bottom we have 1 plus or minus tan of x times tan of y. And the sign is going to be opposite of what we had in the parentheses. This was x minus y. Here we have a plus. X plus y for tangent. Now we have a minus down here in the bottom. So again, make sure you have these memorized. It might take some time to do that, but hopefully those little tips helped somewhat to do that. So now, assuming that we have those mastered enough or memorized enough, we want to now use these to evaluate different trig expressions. So for example, here we have cosine of 30 degrees plus 45 degrees. Or in other words, we're trying to find the cosine of 75 degrees. So what we can do is we can recognize this as being similar to cosine of x plus y, like we had on the previous slide. Instead of x and y, we have 30 and 45 degrees. So if you have that memorized, okay, you can write that out. You have cosine of x times cosine of y. The cos goes together. and then the sign will change, so plus becomes minus, and then sine of x times sine of y. So in place of x and y, we plug in 30 degrees and 45 degrees. So now what we have is cosine of 30 degrees times cosine of 45 degrees minus sine of 30 degrees times sine of 45 degrees. And then from here, we just plug in those values. So we're assuming you have these values memorized from the unit circle. Cosine of 30 degrees would be the square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. Sine of 30 degrees is 1/2, and sine of 45 degrees is the square root of 2 over 2. So then from here, we can simplify. So over on the left side, we would multiply to get square root of 6 over 4. And then on the right side, we would have the square root of 2 over 4. And then we can rewrite this as a single fraction by combining into one fraction with a common denominator. And that would give you the square root of 6 minus the square root of 2 over 4. So what we can do is take any of our identities that we have, and if you're given a problem, whether it be like this with cosine or sine or tangent or whatever, okay, you can see which identity that this matches up with, and then from there, substitute the angle measures with in place of the x and the y. And we're not going to go through examples with each of those because that would take a long time, but the process is going to be the same. So same idea for each trig identity. Now we're going to talk about cofunction identities. So cofunction identities would be basically relating sine and cosine or related functions like that. All right, so first off, we're going to talk about sine. And the first identity is that sine of 90 degrees minus theta is equal to cosine of theta. And you might have actually noticed this when you're dealing with the unit circle, because if you think through the 30-degree angle and the 60-degree angle, and you think through all of the values for those, so like for example sine of 30 degrees, cosine of 30 degrees, and then tangent of 30 degrees. And then you do the same thing for 60 degrees, sine of 60, cosine of 60, and then tangent of 60. We know that the sine of 30 degrees is 1/2. The cosine of 30 degrees is going to be the square root of 3 over 2. And then tangent of 30 would be sine over cosine. So that would be 1 over 2 divided by square root of 3 over 2, which means you multiply by 2 over the square root of 3. And that would give you 1 over the square root of 3. And then sine of 60 degrees, that would be the square root of 3 over 2. Cosine of 60 degrees would be 1/2. And the tangent of 60 would be sine over cosine. So we have the square root of 3 over 2 divided by 1/2, which means you multiply by 2 over 1, which would give you the square root of 3. So the tan of 60 degrees is the square root of 3. So all of this we have used a lot in the past, and that will help us here to maybe remember these different cofunction identities. Because if you take a look, for example, if you look at 30 degrees, so sine of 30, if you replace 30 degrees here with theta, or 4 theta, notice that that would be sine of 60 degrees, which is equal to 1/2. Or sorry, sine of 60 degrees is the square root of 3 over 2. Okay, notice that's equal to the cosine of 30 degrees. Right, you plug a 30 in for cosine. Cosine of 30 is also equal to the square root of 3 over 2. So you see the relationship between the cosine of 30 and the sine of 60. They're the same thing. And that's kind of where this idea comes from. And that's kind of a way to help maybe remember what these cofunction identities are. And the opposite is also true with cosine and sine. So if you do cosine of 90 minus theta, that would equal the same thing as sine of theta. So again, if you plug a 30 degrees here and a 30 degrees here, that would be cosine of 60, that's 1/2. Sine of 30 is also equal 1/2. So again, we can show here very quickly that that statement is going to be true. And it's going to be true for any angle. It doesn't have to be 30 and 60 degrees. It's going to hold true for any angle measure. And then tangent, if we take a look at tangent, all right, the tangent of an angle, if we take a look at, again, 30 degrees, so tangent of 90 minus 30 we're going to try to prove or verify that's equal to the cotangent of 30. Well, tan of 60 is the square root of 3, right? And then cotangent of 30, okay, 30 degrees, that would be the inverse of 1 over square root of 3, which would also equal the square root of 3. So again, we can verify that the tan of 90 minus theta is equal to cotangent of theta. Now the next one is going to be the inverse, or the backwards, of the tangent one. All right, so we can also say the cotangent of 90 minus theta would equal tangent of theta. So we can just kind of switch those around. And then just like sine and cosine were related, we can replace sine with cosecant, and then cosine with secant. And then same thing for cosine and sine here for the second one. So if you take the second one, cosine replaced with secant, sine replaced with cosecant, that gives you your next statement. And then if we take the sine one up here at the top and replace sine with cosecant, and then cosine with secant, we get our last identity right here. So again, these should be memorized, but if you struggle with memorization, if you remember the relationship between the 30 degree and 60 degree angle measures, that may help you to get to these on your own. So now let's take a moment and use what we just talked about to write an equivalent expression. All right, so here we're trying to write an equivalent expression for cosine of 30 degrees. Okay, now we said that the relationship between sine and cosine is that sine of 90 degrees minus theta is equal to cosine of theta. So in place of theta, we plug in a 30 degrees. So cosine of 30 degrees is equal to the sine of 90 minus 30, which would be the sine of 60 degrees. So that would be the equivalent expression to cosine of 30. So that's just one example. You can do the same kind of idea with any of the identities that we just talked about, but that's kind of your thought process you can use for any type of problem like this. Now let's talk about simplifying trig identities, or trig expressions. Here we have sine of x times cosine of 3x plus cosine of x times sine of 3x. Now this is going back to our sum and difference identities with sine and cosine. And you have to think through which identity does this match up with. Well, if you remember your identities we talked about at the beginning of the lesson, okay, we talked about sine of x plus y, how that's equal to the sine of x cosine of y plus sine of y cosine of x. So that's what we're seeing here. Okay, it's comparable to this, where instead of x and y, we have x and 3x. All right, so we see how that compares with what we have over here. So that's going to be a true statement. This would equal the sine of x plus 3x. And x plus 3x is 4x, so we can rewrite this as the sine of 4x. Let's take a look at another example. Here we have tan of 4x minus tan of 2x over 1 plus tan of 4x times tan of 2x. Now again, we have to be able to recognize this as a sum or difference identity dealing with tangent. And this would relate to the identity that says tan of x minus y. So tan of x minus y is equal to the tan of x minus tan of y over, and then 1 plus tan of x times tan of y. So you see how that relates to what we have up here? We can take this identity, and in place of x and y, we have 4x and 2x. So we can write this as the tangent of 4x minus 2x. And 4x minus 2x is 2x, so that would equal the tangent of 2x. So your answer, this expression, can be simplified to become tangent of 2 times x. So we worked with simplifying trig expressions, and now here we're going to work with evaluating trig expressions. And here we're told that tangent of alpha is equal to 4/3, where alpha is in quadrant 1, and tangent of beta is equal to negative 5/12, for beta being in quadrant 4. And we're trying to find the cosine of a minus b. Now to do this, what we want to do is find the cosine and sine of angle A, and then cosine and sine of angle B. And to do this, what we want to do is take this initial expression right here. We know that the angle is in quadrant 1, so we can kind of draw this out like this. This angle alpha is up here in quadrant 1, and the tangent of that angle is 4/3, meaning tangent is opposite over adjacent, so the opposite side from alpha would be 4, and the adjacent side to alpha would be 3. So then we can find the hypotenuse. So the hypotenuse, we can use Pythagorean theorem. So we would do 3 squared plus 4 squared equals the hypotenuse squared. That would be 9 plus 16 equals 25. So, 9 plus 16 is x squared, which would be 25. And then we take the square root of x, x squared, and the square root of 25, and that gives you x equals 5. So the hypotenuse would be 5. So with this information, we can find the sine of alpha. That's equal to opposite over hypotenuse, so 4 over 5. And the cosine of alpha, which is adjacent over hypotenuse, and that would be 3 over 5. So now we have sine and cosine of alpha. We can now find sine and cosine of beta. So we can use this information here. We see that beta is in quadrant 4, so that would be down here, down in this area. And then we'll call it B instead of beta. And the tangent is -5/12. Tangent is opposite over adjacent. So the side opposite of angle B is going to be -5. And the adjacent side, the one next to it, is going to be 12. And then from here, we can find the hypotenuse by using Pythagorean theorem. We have -5 squared, which is 25, plus 12 squared, which is 144, equals hypotenuse squared, which would be x, so x squared. And 25 plus 144 is 169. Take the square root. X would equal the square root of 169, which is 13. So the hypotenuse is 13. And now we can find the sine of beta and the cosine of beta. Sine is opposite over hypotenuse, so we have -5 over 13. Cosine is adjacent over hypotenuse, which would be 12 over 13. So we have sine and cosine for alpha and beta. And by the way, a side note is make sure that we have the correct signs for things. So for example, if you're down in quadrant 3, okay, if you have to find a side length, maybe the opposite or the adjacent side, just make sure it's negative or positive as needed. So like over here in the quadrant 3, adjacent, the adjacent side, the x value over here, this part would be negative, and also sine, the y value would be negative as well. So just take that into account when you figure out sine and cosine. And now from here, we see that information typed up, and now we can use the cosine of alpha minus beta identity to determine what that is equal to. So we can use our identity that says that cosine of a minus b would equal cosine of a times cosine b plus sine of a times sine of b. And then in place of the a and b, or alpha and beta, same thing, you can plug in what we figured out. Okay, so cosine of alpha, we found that to be 3/5. So plug a 3/5 in place of cosine of alpha. And then cosine of beta is 12/13. Sine of alpha was 4/5. Sine of beta was -5/13. So we multiply and then add those together. And we see that typed up down here. For the first part, we'd have 36 over 65. Second part, we would have -20 over 65. So then you add the negative, so we subtract, and 36 minus 20 would be 16. So we have 16 over 65 as our solution. So we've demonstrated how to evaluate a trig function. And now we're going to verify a trig identity by using the identities we talked about in this lesson. So here, for example, we have sine of 3x over x plus cosine of 3x over sine of x plus sine of 3x over cosine of x is equal to the cosine of 2x over the sine of x times cosine of x. So what we can do is we can use the guidelines we talked about in the previous lesson to kind of get us through this. And our goal is to look at the most complicated side, which in this case would be the left side. And we're trying to write this as a single fraction that looks like what we see on the right side. So we can do that. We could try to write this as a single fraction. And to do that, we would need to find a common denominator. Well, we see sine of x and cosine of x. If you multiply those together, that would give you your least common denominator. So we do that for both fractions. We're going to rewrite with this new denominator. The first fraction, we had sine of x. Now we have cosine of x as well. So we have to multiply the numerator by cosine of x also. So we have cosine of x times cosine of 3x. And then the second fraction, we had cosine of x, and now we have sine of x. So we need to multiply the top by sine of x as well. So now we have sine of x times sine of 3x. And then we can write this as a single fraction. We would have the cosine of x times cosine of 3x plus sine of x times sine of 3x. And all that is over sine of x times cosine of x. Now the only thing we need to do from here is take care of the numerator, because the denominator is the same as we see on the right side. We just need to take care of the numerator. So we need to identify this as one of our identities. So this one would go along with the cosine of x minus y identity, right? Because that is equal to the cosine of x times cosine y plus sine of x times sine of y, where here instead of x and y we have x and 3x. So that's what we can do. We can do x minus y, so that would now be replaced with x minus 3x. And that would give you negative 2x, right? We have cosine of negative 2x, which you don't actually want the negative in here. Okay, we can actually take care of that and realize that cosine, so cosine of positive x, is going to be the same as cosine of negative x. Because cosine is positive, it's going to be the same value on the right, or in quadrant 1 or quadrant 4. So that's the same thing as cosine of 2x. So this would be cosine of 2x on the top, so cosine of 2x, and then over sine of x times cosine of x, which is exactly what we're trying to get to. That was the right side of that equation. So this one has been verified, and this one is complete. And one thing to point out too with this, you could have actually, if you look back here, okay, we could have switched the order. So instead of cosine x, cosine 3x, we could have done 3x and 1x, and then sine of 3x and sine of 1x. So if you do that, we'd have 3x minus 1x instead, which would give you right away the cosine of 2x. So either way, we get the same thing, and we have verified this identity. Now be aware that when verifying different trig identities, there's not really any two that are going to be identical. So we can't really show you every single possible scenario that you'd come across. But the idea is to use these identities and maybe do something like we did here, combine into one expression. Or sometimes you might find that you need to separate. Like for example, if you had cosine of 2x, you can think of that as cosine of x plus x. And then you can use your identity, the one that says cosine of a plus b is equal to cosine of a times cosine of b minus sine of a times sine of b. So you can use that to separate, and you can write that as the cosine of, instead of a and b, we put x and x. So cosine of x times cosine of x, and then minus, then we have sine of x times sine of x, which would give you cosine squared of x minus sine squared of x. All right, so we could do things like that, and we could, depending on what we're trying to prove, you can then go from here and take that and write that as 1 minus sine squared of x, and minus that sine squared of x, and you can get 1 minus 2 sine squared of x. So all sorts of things we can do from that point, but just want to point out the fact that we could separate something like this as x plus x and then get something from that. Now, one more thing to take care of in this lesson, and that is called a reduction formula. So with the reduction formula, what we're doing is we're going to take something like this, where we are told to write as a function only involving cosine of theta for this right here, where k is an integer. So we're taking this thing, this expression, and we want to rewrite this as a function only involving cosine of theta. All right, so we're taking this and reducing it into something else, and that's where the name comes from. All right, so when you do this, you have to think through this part right here, what effect that has, because you're starting with an angle. Okay, so it may be helpful if you draw this out. So you have an angle, we'll call that theta. All right, and then we're adding 2k plus 1 times pi, where k is an integer. So if you plug in numbers for k, so say you plug a 1 in for k, we would have 2 times 1 plus 1, which would be 3. So we have theta plus 3 pi. If you plug a 2 in place of k, we have 2 times 2 plus 1, which is 5. So we have 5 pi. Then you plug a 3 in, we'd have 7 pi, and etc. So now we got to take a look and see how does these different angle measures affect the cosine of theta. So we're adding here, first of all, 3 pi. So 3 pi would be going around once, that's 2 pi, plus another pi would take you over here. So if you go around from here, 3 pi, it would be 1.5 rotation or revolutions around this. That would take you over here to this location. So in this location, okay, the absolute value of cosine would be the same, but on the right side, we have cosine is positive, but then down here, down in this location, cosine would be negative. So all of this is going to make cosine, so the cosine of theta is going to make that into a negative. It's going to change the sign. So all of this can be written as negative cosine of theta. And then the 5 pi, if you add another 2 pi to get to 5 pi, it's going to be back to the same location. So we have the same thing each time. So we can reduce the initial formula to get negative cosine of theta. So we have the correct answer, but let's show you quickly one other way where we could get the same solution, and that is by using our cosine identity, the one that says that cosine of x plus y is equal to cosine of x cosine y minus sine of x times sine of y. So if we use that, notice here that x would be the theta, and then y would be this expression over here. So we can rewrite this as the cosine of theta. We'll type that up here, cosine of theta, and then instead of cosine of y, we now have cosine of 2k plus 1 times pi, and then minus, and instead of sine of x, we have sine of theta, and then instead of sine of y, we plug a 2k plus 1 times pi in place of y. All right, so it's still kind of the same thought process because we still need to figure out what is the cosine of 2k plus 1 times pi, and what is the sine of 2k plus 1 times pi. So again, kind of same logic here. So we start with pi. So pi would be over here in this location. And then we multiply that by 2k plus 1. So if you plug a 1 in place of k, we have 2 times 1 plus 1, which is 3. So we'd have 3 pi. And then if we have, if we put a 2 in place of k, 2 times 2 plus 1, that gives you 5 pi. So each time it's going to be in the same spot. All right, so it's going to be over here. And same thing for over here, sine as well, as the same angle. So basically we're trying to figure out now what is the, so we have cosine of theta, and then what is cosine of 180, or pi, same thing. And then over here we need to figure out what is the sine of pi, or 180. Well, cosine of 180 is negative 1. So we have negative 1 times this cosine of theta. And then over here, sine of 180 would be 0. So we have 0 times sine of theta, which is 0. And that would give you negative 1 times cosine of theta. which is the exact same thing we got earlier, right? Negative cosine theta. But this is just another way that we can verify the same thing. And this concludes our lesson for today. We will see you next time.